All right, let's talk about beta decay. So remember, there are two different types that you probably notice in the simulation. Negative beta, which is an electron. Okay, so negative beta, and positive beta is a positron. It's got the same mass and the same charge as an electron, but its charge is positive. It's actually an electron's antiparticle. And if they get too close together, they'll be attracted and they will annihilate each other. Their mass will turn into energy using Einstein's E equals mc squared, which we'll talk about next class, I think. All right, so let's take a look at negative beta decay and do an example equation for this. So let's start with carbon 10. Carbon 10 has 10 nucleons, 6 of which are protons. And remember, it's the proton number, the atomic number that defines an element. So carbons always have 6 protons. All right, so in a beta minus decay, there's a beta particle that's emitted, and we represent that with 0 nucleons and the equivalent of -1 proton. Okay, to make the nucleons the same on both sides, if we have -1 beta here, -1 atomic number, and here we've got 6, to make the right-hand side of our equation equal to 6 for the atomic number, this element needs to have a 7. Okay, and then 10 on this side, 0, so this also needs to be 10. And the element that can have 7 protons and 10 total nucleons is nitrogen. Now, when this reaction happened, they could detect an electron, right, a beta minus particle, because it has charge. They could detect the nitrogen because it's a decently massive element. But those two particles were moving in such a way that it broke the law of conservation of momentum. And I'll talk about this on the next slide, but there had to be another particle to not break a physics law. And so it was hypothesized that it was a particle that had very, very small mass, had no charge, so it couldn't be like detected in a mass spectrometer or anything like that. So it had to be tiny, and it had to be neutral. There was already a neutral particle called a neutron. They were kind of playing around with names of particles. There was this big neutral particle, right, what we call a neutron, and there was another little neutral particle that some other scientists had also proposed calling a neutron, and there wasn't really a way of distinguishing them without, like, clearly yet. This was happening back in the early 1900s, like the 1930s-ish, and this work was being done primarily by, like, Wolfgang Pauli, Enrico Fermi, actually, and they said that there had to be a neutral particle. So we're going to add something to this equation. This is the Greek letter nu. And we're going to put this line on top here. This has essentially no mass. So we can write it like this. And this thing is called an electron antineutrino. Okay, so they're kind of throwing around words of what this particle should be called. This is officially now called an electron antineutrino, but it was actually Enrico Fermi who, in Paris, I believe, at an academic symposium, was the first one to write neutrino as a word in an academic paper and mention it in an academic presentation. It was actually through a conversation with Edoardo Amaldi, an Italian physicist, where Amaldi can distinguish the two neutral particles, a neutron, and then the smaller neutral particle is a neutrino, right? Using the Italian diminutive INO, just meaning little. So neutrino literally means little neutral one. Okay, and there are a bunch of different types of neutrinos. There are neutrinos and then there are antineutrinos. Antineutrinos are the antiparticles of neutrinos, and just like electrons and positrons, when they come together, they annihilate to produce energy. Okay, so electron antineutrino is the particle that works to fulfill this equation. Electron neutrino is the type that you'll see in both positive and negative beta decay. When you're working with negative beta decay, you'll always see an antineutrino. Okay? And then for positive beta decay, let's say we're working with a different isotope of carbon, carbon 11, and you would see beta decay, and then you'd have a +1, and then what would you have to have here? Well, to make 6, we've already got +1, and so this element would have to have an atomic number of 5, and a mass number would still have to be 11, right, to make the two sides equivalent to each other. And the element that has 5 protons, boron, I believe. And then there's also an electron neutrino. That's an electron neutrino. Oops, that's a TRINO. Okay, cool. So if you have positive beta, so positive beta and an electron neutrino. Okay. So here's just kind of a summary of how to deal with positive and negative beta particles. So you can actually, this is the equation that they've got up here with the example is just for negative beta decay, but we can apply the same idea to positive, just changing this to a plus and this to a minus. Okay, so betas are electrons or positrons. They are way less ionizing. Remember, alpha particles could ionize 30,000 pairs per centimeter. Betas can only ionize about 30, so they're way less ionizing. Okay, and that's the ionizing radiation that is dangerous to us. They are directly ionizing, so they come in contact with particles and ionize them. They're shielded by low mass number materials, so plexiglass, clothing, gloves. Remember, alpha particles can be shielded by skin. Betas can be shielded by clothing. But alpha particles have a discrete amount of energy. Interesting thing about beta particles is they have a spectrum of energies, which is super interesting. Because beta particles have very little mass, they can travel really far, like about 20 feet or so sometimes. And they could be damaging to our exterior because they have such high energy and they can travel so far. Okay. All right, so here's a little bit more information about that neutrino. Okay, so remember the law of conservation of momentum says that the total momentum before and after a collision or an explosion has to be consistent, right? So if you've got a parent nucleus Okay, and this isn't a momentum vector. This is just, we're going from this parent nucleus to the products. So we'll say this parent nucleus has a momentum of 0, right? What we would expect, they were able to detect 2 particles coming off of the parent nucleus, right? You've got your daughter nucleus right here, and then your beta particle. And what you'd expect if you've got a parent nucleus just sitting still, hanging out, after it decays, the 2 particles that they detected, right? If there were only 2, they would come off and they would have equal momenta, but in opposite directions, right? The daughter nucleus would be going in one direction with a smaller speed, and the beta would be going in the other direction with a larger speed because it has less mass. But that's not what they saw, right? What they saw is the parent having no momentum initially, and then after the decay, they saw 2 particles going at like angles, and they're like, whoa, we just broke physics laws somehow. Like, what's up, law of conservation of momentum? But as a result, they're like, there must be another little particle that we can't detect because it's probably neutral, right? And if we add the momentum of our parent or our daughter nucleus and the beta particle, right, there's a net momentum that's kind of in that direction. And so they hypothesized that there must be another particle that had a little bit of mass and thus some momentum heading in exactly the opposite direction, okay, to make the total momentum of this whole thing 0. It had to be neutral because they couldn't detect it with their detectors, and it had to be a tiny, tiny little mass. Okay, so that is kind of how the idea of a neutrino was born. Okay, so the last type of decay is called gamma decay, and actually alpha particles are as a result of a similar phenomena to gamma decay. They come from a nucleus, and because both alpha and gamma particles have discrete energies, it was hypothesized that just like electrons have discrete energy levels, so does a nucleus, right? And so alpha and gamma particles are emitted by a nucleus, have these discrete energies, and so the nucleus must also have energy levels, just like electrons have energy levels. Okay. So this is kind of a similar graphic to our electron energy levels. If you've got, I think this is called a Americanium nucleus, right? It can decay into specific energies and through several processes. There are several energy levels, several gamma particles that can be released, and each energy level has a certain amount of energy. And so we want to be able to calculate the amount of energy and the wavelength of the gamma ray emitted from the transition energy level down to 1 or 0. Okay, so I'm going to pause this right now, and we're going to talk about this more in the next video.